role of a bulletproof vest is to absorb the impact and prevent penetration to the body of projectiles. In the past, many different materials were used, but a common property was high hardness and tensile strength. The material that stood up for centuries and is still used today is steel. With only a few millimeters of thickness, steel is extremely effective at stopping projectiles. By finding the right amount of hardness and tensile strength, the steel will deform under the stress applied from a projectile but will prevent penetration. In terms of alternatives, the past 50 years have seen the rise of ceramics and Kevlar. By layering the hardness of the ceramic plates that absorbs impact with the high tensile strength of the Kevlar that prevents penetration, an effective body armor was created. Some other considerations when creating body armor is the weight. Bulletproof vests are often used by the military, and when in engagements, mobility is an important consideration for survivability.
From the phase diagram above on the slides, we can see the properties of steel can contribute heavily to the protection from bulletproof vests. Rifle-resistant vests usually contain 3 layers of materials that utilize different properties to stop bullets. First, the Kevlar layer is used to help stop penetration and deflection of bullets. The second layer, a steel plate, is used to absorb and distribute the load of the bullet, usually made from AR-500 steel. This type of steel is made by adjusting the manufacturing processes of rolling, finishing, and heat treat. Finally, a ceramic plate is utilized due to its strength to stop the bullets entirely and redistribute the load further before the force is felt by the person wearing the armor. Ceramic is used due to its hardness and lightweight combination of carbide materials. All 3 layers have different flaws, but combined gives the best chance of survival and lower chance of deflecting bullets or shrapnel due to the Kevlar.
When it comes to steel, there are thousands of options available, each serving a unique purpose. In the case of bulletproof vests, however, one of the most common types is known as AR-500 steel. This type of steel contains about 0.31 weight percent carbon, which offers high enough strength to stop a bullet, while also having high impact strength, which allows the material to absorb a large portion of the force from the bullet. When it comes to the phase calculations for this type of steel, it is important to notice where the eutectic point is, which in this case is 0.8 weight percent. Since 0.31 is less than 0.8, this is a hypoeutectoid alloy. Because of this, we know that the composition of the material will be ferrite and pyrrolite, the calculations of which are shown. The first figure shows the phase diagram for steel, which is used to perform the phase calculations. AR-500 isn't the only type of steel. In fact, every different composition of steel can fall into 3 different categories. The first is low carbon steel, where the percent carbon is less than 0.3%. This type of steel tends to be more ductile, however has low strength. The next is medium carbon steel, where there is 0.3 to 0.6% weight carbon. These steels tend to be less ductile than the low carbon steels, but are much stronger and have small benefits from heat treating. Finally, there is high carbon steel, where the weight percent carbon is greater than 0.6% weight carbon. These steels tend to exhibit more brittle properties, yet have the highest strengths and benefit the most from heat treating. In the second figure, there is a depiction of stress strain curves of the 3 different types of steel. We clearly see that the medium carbon steel is the toughest type, meaning that it absorbs the most energy, which is the property that is most useful in being resistant to bullets.
Bulletproof vests are made of a material called Kevlar. Kevlar is a very strong material with a tensile strength of 3,620 megapascals. Kevlar also has a high toughness, being 5 times stronger than steel. Bulletproof vests need to be protective, so it requires a strong material to ensure people's safety. Kevlar is made of manufactured plastics, using several layers to remain lightweight but still be protective enough to stop a bullet. It also has good chemical stability, making Kevlar a good choice for bulletproof vests because it ensures that the bonds won't break easily. Kevlar doesn't corrode or break down, but it can fail from fatigue over long periods of time. Some of the main causes are too much sunlight, long exposure to strong acids or bases, and of course, bullets repeatedly hitting the protective layers of the vest. Kevlar can fail from too much sunlight because the UV rays break down the bonds and make the material weaker, which makes the vest less effective. It can also fail from strong acids and bases because plastic reacts with the acids and bases, and the chemical reaction makes the vest less effective.
Bulletproof vests consist of Kevlar with steel plate reinforcement. Within Kevlar, there are axially oriented hydrogen bonds within the microstructures. These microstructures are interconnected by van der Waals forces. The image on the right illustrates small gaps between the atoms, which are called interstices. These interstices are filled by carbon or nitrogen atoms. Increasing the strength of the material is important to the vest's ability to deflect bullets. As more and more carbon atoms enter the small gaps, the atomic lattice strains, which thus requires more force to deform the material, which ultimately increases the strength. The composition of steel consists of iron and carbon atoms. Each steel has slightly different properties, depending on the percentage of carbon and iron in each structure.
Although Kevlar is ideal for ballistic protection, it is prone to degradation when encountering water or UV light, making its shelf life usually 3 to 5 years. In recent years, better ballistic performance and more stable nature of ultra-high molar weight polyethylene is gradually replacing Kevlar, becoming the mainstream material for bulletproof vests. It has extremely long chains, and the longer chains transfer the load more effectively to the polymer backbone by strengthening the intermolecular interactions. This results in a very tough material with the highest impact strengths of any thermoplastic available. The only drawback for this fiber is that it is not resistant to high temperatures. Above 70 degrees Celsius, strength will drop, while Kevlar can withstand temperatures of 400 degrees Celsius. Even more, when suddenly encountered above 900 degrees Celsius, Kevlar will be directly carbonized, forming an insulation layer. For the prevention of explosion damage, still Kevlar is more effective.